about orbits, and that brings us to Kepler. So just a little bit of history, and I gotta like flesh this out because I feel like it's not comprehensive, but we'll start with Ptolemy. He had this, so we used to be very self-centered on Earth. We used to think Earth was the center of the universe. Some people still think they're the center of the universe. You've probably met some of them. But no, the geocentric means Earth is the center. Well, this provided a big problem for doing the math because, have you guys ever been out to the desert and looked at the stars? Like a place where it's really dark? How many stars can you see?
A lot.
Yes, the correct answer is shit ton. There are a shit ton of stars. How many stars do you see when you like go outside in regular cities and look up? Like
Zero.
sometimes one, but it's a satellite or a plane, yeah. And so you gotta think like people in the ancient world, what did they not have at night? Light pollution, because you used to have to like, there's a really interesting podcast I was listening to that's talking about how many hours an average person had to work to provide 1 hour of light at night. And it used to be like you'd have to work all day to get like 1 hour of light. Now you could just like have like an LED flashlight on your phone that like wouldn't have been thought of. Anyway, the great thing about living in the ancient time wasn't dying of dysentery or like any of that stuff. It was there was no light pollution. So if you wanted to be an amateur astronomer, you could just look up and you didn't even really need lenses. It was really cool. If you want that experience, you have to go to a dark sky location. Like I think Anza Borrego is actually a pretty good dark sky location. But people spent a lot of time, because also there wasn't as much to do because they didn't have Netflix, and they would just look at the stars and like be like, I saw that star, and now it's over there, and now it's over there. So the other thing that moves in the sky, planets. Have you seen a planet in the sky before?
I didn't.
Yes.
I heard about it. I never
You've
seen
heard
it.
about planets?
Yeah.
Well, it's actually pretty simple. You can, if you go to like astronomy.com or you get any of the astronomy apps, it'll tell you when there's planets in the sky. But there's two cool planets, in my opinion, for looking at. The one that's easiest to spot is Mars, because what color is it? Red, and you can actually see that it's red from here, which is insane. So there's Mars. There's also, if you have any kind of telescope, looking at Saturn is cool because you can actually see the rings. You can see them with like a shitty telescope. If you have a good telescope, they look really cool. You can even see its moons. Okay.
There's the blue one.
What?
Isn't there a blue one? I forget which one that one is.
Neptune.
Neptune?
Yeah.
Fun fact, which planets can you only see at like sunset and sunrise? Which ones are between us and the sun? Thank you for that smart ass answer. Mercury and Venus. Mercury and Venus are between us and the sun, so they're really hard to see when you can't see the sun because they're always towards the sun. Because
How would you see them if it's night? Do people just think they didn't exist?
no, you see them like at like the beginning of the night and then they go away. Yeah. Anyway, so big side note. Here is a video of the apparent motion of Mars. So this is just imagine you take a picture at the same time every night looking at Mars, okay? And we're just picking some dates over a course of several months, okay? And it says the dates, I think, but hang on. So these are the dates. So this is September 11th, 2009.
Where's it at?
So this is a 20-day interval. It hasn't started yet. So October 1st, are you seeing it? This thing that's moving. Okay. So it's going this way. Still going this way. Now we're in December. And now in January, it's moving backwards. Still January, late January, moving backwards. February, moving the other direction still. March. Now it's moving forward again. And still moving forward. I should sped this up more. And so remember, this is all relative. What we've done is all this stuff moves and moves and moves, but what we've done is compared to the fixed motion of the stars, right? If you make the stars still and you track the motion of the planet, this is what it looks like. So it goes forward and backward. And so this is the difference between like being able to describe something mathematically and having it be true, okay? So sometimes we come up with models that work, like we can predict things mathematically, and that doesn't mean we know really what's happening. It just means we have a way of predicting based on previous data, okay? So there's a really interesting story here where, here, they sped it up. This is what's called, what like ancient astronomers called a retrograde motion, okay? So when your friend says that like Mercury is in retrograde or whatever it is people who like to talk about astrology say, that's what they mean, although they probably don't know that's what they mean. It means it's the time when it's going backwards because astrology is made up. But it's based on some actual astronomical stuff. And so, and we trace it out. So this is the path over several months. And this doesn't make a lot of sense if you're the center of the universe, okay? If we're at the center of the universe and everything's moving around us, things shouldn't turn around and go backwards, okay? And so what astronomers did and mathematicians, they got together and they created basically a Fourier series to predict the motion, and it was actually very accurate. They could actually predict several years in advance like where things would be, but it was really, really complicated math. And then if you don't put Earth at the center and you put the sun at the center and things move around the sun, it really makes sense. Because think about being on a racetrack where everybody's going at constant speed but different speeds, okay? Like things can pass you and then you can pass them because you're on a different radius track. And that makes a lot more sense from a conceptual standpoint, but mathematically, both descriptions worked, okay? So testing your theories with math includes like making sure that the actual theory makes sense. So there's a way to mathematically describe being at the Earth being at the center of the universe that's very accurate and wrong, okay? And that's why science has to constantly like check things, test them, and like try again. The funny thing about that is when we finally went with the heliocentric model, which is just Greek for the sun's in the middle, okay? The math was so shitty that, because it was a new model, the one that was wrong actually worked better at predicting stuff for a little while until they sort of figured out how to do orbits better because of, I don't think they also like assumed all orbits were circles and they're mostly a little bit elliptical, okay? All right, any questions about this? So Copernicus has the heliocentric model, and I feel like we're leaving some people out because there's also like the golden age of Islam, and they had astronomers that had some similar views at earlier times, and I don't have that recorded, and that's some research I'm doing, but we happen to have these recorded because Europeans. So then we get to Johann. This is, I don't speak Dutch very well, but I'm sure his name sounds like a sneeze, but this is Kepler's first law. And he has three laws, just like Newton. They're not as useful for us, but we're gonna just go over them for the heck of it. The orbit of every planet is an ellipse with the sun at the focus, okay? So looks something like this. This is a big exaggeration. Most of the orbits, aside from like the highly elliptical ones like Neptune, are pretty circular. They're pretty close to circular. Not mathematically close enough to exactly predict orbits, but close enough that like it doesn't deviate that much from a circle, okay? Which when you think about it, this is a side note, astronomy is like a crazy thing because you're like, why are all the planets in a single plane, like all orbiting in circles? That's weird. There's probably some reason. Okay, you have to take a different class for that because I don't know. But in any case, this is how you create an ellipse. That's what the two foci mean. That the length of this thing doesn't change but the relative lengths of each piece change, okay? But yeah, this plus this always equal the total length. You can do this at home with pins and string. You can make your own ellipse. We tried it earlier, yes. Okay, here's a quick thought. So here's some answers to this question. This person says because of the Earth's elliptical orbit, it's closer to the sun during the summer. Is this true or not true?
That's a good question.
You just hear hand raised, or you're just doing this?
So I'd like to believe it was true.
Talk about it and then we'll ask again.
If I was lied to like 10 years ago, then
So what's your thoughts?
because that's what they told me. They're like, it's the sun's closer, then it's warmer.
So,
But
not
I'm
sure,
pretty sure it's
but
because
I'm
we're on
pretty
an
sure it's just
axis.
because we're not, like, the way the Earth rotates,
Not
we're
the
not
actual
rotating,
orbit.
it's rotating on an axis.
about the
So we're not facing
It's
the
on this
sun during,
it's tilted, and so like
we're not facing the sun during.
when the
During
thing
winter.
Yeah, during
moves,
winter.
it like moves
The other
it.
side of the Earth is facing, which is why we have seasons in different parts of the Earth.
Yeah, makes sense. Yeah. Well, I feel like in the middle, like the source is from.
Wait. So
Like we're
the
like
thing-
like in
the axis is-
we're not like
I don't think the actual
we're kinda like between like close to the sun and far away from it.
Yeah, we're like because of our elliptical orbit. It's not that we're
Because
necessarily
like if the axis is like this, we still spin around this way. We don't go like this way with the axis. Of, like we spin around the axis.
We're like, this is the sun, and we're like
But
this.
like yeah, but like when we're going around the sun, does the vertical or the diagonal axis like change this way? It's constantly like this, right? So
No, it's like this.
yeah. Wait. Okay.
Yeah, but isn't
It doesn't like keep like
It doesn't, like-
facing it. Wait, yeah, that's why it's summer.
It doesn't do this.
Yeah.
Yeah. Okay. Okay. Is it because of the elliptical orbit? Yes or no?
No.
No.
We decided no. What did we decide it is because of?
The axis.
The tilt of the Earth, okay? So the sun is in the middle. Our Earth's orbit is almost, like it's elliptical, technically, it's not a perfect circle, but it's pretty damn circular but like that's how strongly I feel about the circularness of Earth's orbit. But what does happen is, here, sun, Earth, okay? This thing is tilted, so this part of the Earth is tilted more towards the sun at this time, right? When it gets over here, it's still rotating, but it's rotating around this axis, okay? So like this rotates, but it doesn't, like it's not like it flips over here, okay? So at this point, you can see the blue stuff is getting more sun. At this point, you can see the pink stuff is getting more sun, okay? And you can think about it this way, like the sun in the summer, why is it so much hotter in the summer?
Because it's hard to.
Where is the sun though? Like in the middle of the day, if you're just looking for the sun, where would you look? Straight up. In the winter, it's kind of over to the side, okay? And because of that, you end up with less. Think about shining a flashlight directly onto something and then tilting it this way. Your density of light is a lot stronger in the summer because it's more directly on. If it comes in at an angle, it's sort of like a cosine theta situation, right? So you get light cosine theta, and cosine theta is always less than 1. So if you have light coming in at an angle, the total intensity is the intensity cosine of the angle that it's coming in, and so it's weaker. Okay, so we get weaker sunlight in the winter time because of the tilt of the Earth's axis, and like full on in your face sunlight in the summertime, and that heats everything up, including water, which retains heat really well because it has a high heat capacity, and that's then seasons happen. Yeah. If you want more detail on that, take a completely different class on like weather or geology or something, because now you've reached the whole extent of my understanding of weather. Okay, there's also some fluids. I know about the fluids. We'll talk about the Coriolis force in a minute. Kepler's second law, we're not gonna be tested on this, I just think they're cool, so we're just gonna go over them. The rate at which the area is swept out as an object order orbits is constant. So for instance, even this is obviously a highly elliptical orbit, which most orbits aren't, but like this is 1 month, this is 1 month, they have the same area. You're moving faster as you get closer to things, remember, because the radius being smaller means faster motion, and you're moving slower as you're out here. So if you have a comet that goes around the sun, right, it's gonna move really fast while it's by the sun, and then it goes way out and goes slow, and then it comes in and goes fast, and then it goes way out and goes slow. And you can calculate the angular momentum. This should look semi-familiar. But here is an animation of all these little pie slices represent the same amount of time. Okay? You can see it's getting, the green thing is speed. So you can see the speed gets bigger as you get closer and smaller as you get farther away. Okay? The only Kepler's law we really deal with is Kepler's third law, which is annoying, but here it is. This is the period. This is the radius. This is the mass of the object you're orbiting, and this is the gravitational constant. So this is sort of describing what we just saw, but it says period squared is proportional to radius cubed. Okay? Oh, and this is pi. Do we want to do that? We're just going to do a clicker question on this.
Yeah.
Did you write down the equation? I'm gonna get it right.
Oh, man.
It's okay, I can't tell which one was you. Alright, if you haven't voted, please do. Good. The chat has stopped voting. Alright, it's either B, C, or D. Please discuss. You may need to do a little bit of
About
math.
this one, what will you pick?
I put C.
I have no freaking clue, so.
I'm really hoping you get this all right, otherwise I have to like do math for you.
Very C.
Yay! Okay, good. We figured out ratios, and the answer is C. So I'm not going to do the ratio again since we already did one earlier this time. Okay.